Hello guys, welcome to class. I'm so glad to have all of you here for this R programming course. And we are gonna kick things off today with a course introduction. Yes, this is gonna be a programming course with a focus on business analytics and data science. And the media we are gonna use to instruct computers to solve business or data problems is the R language. I think everyone who is willing to take this course is somewhat committed to the idea of business programming, or more concretely, using the programmatic approach to tackle business analytics problems. So I will not spend much time on motivating you to learn programming, as I usually do for some introductory level programming courses. But here I would like to first talk about what are good attitudes that lead to success in a programming course. Like in other programming courses, there will be various situations along the way in R programming. No matter how skilled you are, failures and bugs are sort of inevitable with your programs, and frustration is totally normal. So learn to live with them. When you encounter a code failure and cannot debug it in minutes, take a breath and be patient. Or do something else and then come back to it with a clearer mind and better mood. But you should never avoid problems and give them up. The obstacles you've encountered actually pinpoint what you should learn to go further with your practice. Learning programming requires a ton of practice. Just as it's easier to learn English conversations in an English-speaking country, because you practice everywhere you go. Practice is essential in learning programming. And programming is not just about knowledge of syntax and grammar. Rather, it is a skill that needs both knowledge and thousands of repetitions. In addition to making abstract concepts tangible, practice also gives you chances to find unnoticed particulars and identify potential misconceptions. That's why there will be 9 in-class programming exercises, the provision of which is due to our emphasis on practice. Please be prepared for getting your hands dirty. And also note that our teaching team will always be on call to walk you through any difficulties you may face. Now it's time to start our R programming journey. I would like to begin with a very brief history of R and an overview of R's features. Basically, R is a dialect of the S language. Okay, then you may wonder, what is the S language? So S is a language that was developed at the now defunct Bell Labs, and it was initiated in 1976 as an internal statistical analysis environment that people at Bell Labs could use to analyze data, so as to avoid doing some statistical routines over and over again. At that point in time, they wanted to create an interactive environment to look at data and do basic analysis. Then as the needs became clearer and the sophistication increased, they can slide gradually into programming and developing their own tools. The system would promote the transition from user to programmer. This basic idea was inherited by R, which is an implementation of the S language. R is a relatively recent development. The first announcement of R was made to the public in 1993. It was developed by statisticians as an interactive environment for data analysis. Many users think of R as simply a programming language. I prefer to term it as an environment within which great statistical and graphics techniques are implemented in a powerful language, which is suitable for both interactive exploratory work and new tool developments. R's functionalities can be easily extended via packages. In R, the package is a fundamental unit of shareable code and bundles together self-contained code, data, and documentation. As a language, R is a hybrid language, which embraces both functional programming and object-oriented programming paradigms. These terms could be abstract to some of you. Actually, a programming paradigm is just a style of building the structure and elements of a computer programs. So simply put, functional programming builds programs with functions, while object-oriented programming builds programs around the notion of objects. R's syntax and structure have been explicitly designed to formulate expressions about statistical objects. But at its heart, R is primarily a functional programming language. So it follows a style of problem solving centered on functions. As a result, R has a large vocabulary of built-in functions and also contains many tools for creations and manipulations of functions. R is open source and licensed under the general public license. It makes R what we call free software. So R doesn't cost any money. You can download the entire software from the web. Specifically, the comprehensive R archive network. That's a place for all things about R. There's a very active and vibrant user community. The user community is one of the most interesting aspects of R. It's where all the R packages come from, and it creates a lot of interesting features. On CRAN, right now there are about 15,000 plus packages. These packages are contributed by users all around the world. CRAN has a number of restrictions and standards that have to be made in order to get a package published on CRAN. So the packages that you download have to meet a certain level of quality. For example, there has to be documentation for all the functions that are in the package, and they have to make sure that they pass a certain number of tests. So CRAN has a lot of different packages written by users, and the number is really increasing every day. But the core software of R is actually quite lean. A fresh installation of R only supplies about 8 packages, which we refer to as base R. Base R has all fundamental functions that we need to run the R system, and a bunch of other packages which include, for example, stats, datasets, graphics, etc. And there are many more packages available through the comprehensive R archive network. We can add them on an as-needed basis, and R makes it very easy to install packages from within R. Just type install packages, followed by parentheses, taking the name of the package we want to download and install. To use the functionalities provided in an installed package, we need to first load it into the current R session with the library command. Then all functions and datasets in this package are readily available to use. R includes a help system to help you get information about installed packages, all functions or datasets contained in an installed package. To get help on a package or function, you would type help, followed by parentheses taking the name of the package or the function, or equivalently, type the shorthand, question mark, followed by the name. If you have experience with other programming languages, you may at first find R very alien. Actually, R has a reputation of being hard to learn. Some of that is due to the fact R is a specialized rather than general-purpose language, with its design decisions geared towards statistical computing. Some is an unavoidable byproduct of its extreme power, flexibility, and extensibility. In R, there are too many things for accomplishing the same goal. Each perhaps provide slightly different approaches. Recall that R is essentially based on a 50-year-old technology, the S language developed in the 70s, and thereby have accumulated a lot of legacy code. In the early days, a key feature of R was that its syntax is very similar to S, and even nowadays, it still keeps some commands for compatibility with S, like the mode function. Another reason is that everyone is free to add new capabilities to R. The resulting code for different R packages may overlap, and it may take a while for users to figure out subtle distinctions between similar functions. R is continuously evolving, and different versions have been released since 1993. Over this course, base functions have grown organically with contributions from multiple authors. Since R lacks a consistent naming convention, names used by these base functions are not very consistent, sometimes even misleading. You will see names for base functions like names, colon names, that both retrieve the colon names of a data frame. And despite having this weird period, row names works exactly the same as these row names on a data frame. For this pair of functions, row sums gives sums of different rows on a matrix of data frame, while row sum gives colon sums based on some grouping rule. Yes, you didn't hear it wrong. It gives colon sums. The last examples concern inconsistent parameter names. These two parameters both control result simplification for two members in the same base function family. When it comes to and-on packages, things involve much more complication. Almost every useful library in R is defined with its own interface pattern, so every library has its own learning curve. So when using a function, you should read the documentation carefully to figure out what a function actually does. R's help files are often thorough and usually contain many working examples. However, they are definitely not written for beginners. My favorite example of this is a help file for one of the first commands that beginners learn, print. The R help file for its print function says, print prints its argument and return it invisibly while invisible x. It is a generic function, which means that new printing methods can be easily added for new classes. The reader is left to wonder what invisible output looks like and what methods and classes are. You may need to look for help on them separately. By listing these aspects that make R hard for beginners, I hope this discussion can help prepare you for some of the pitfalls that you are likely to encounter. But more importantly, I hope you will become aware that many of these problems are due to R's unique nature, as well as its power, flexibility, and extensibility, and they actually come with benefits. So be patient with them. At its heart, R is an elegant and powerful language, well tailored for data science since its very beginning. To even get started in data science with a language like Python, one must learn a lot of stuff not in base Python. For example, NumPy, Pandas, and Matplotlib. By contrast, R has deep-seated language support for data science. Data and statistical analysis capabilities and basic graphics are built into base R. A novice can be doing simple data analysis within minutes. R also offers a massive set of packages for statistical modeling, machine learning, and manipulating data. Whatever model or technique you are trying to use, chances are that someone has already tried to do it and you can learn from their efforts. Moreover, researchers in statistics and machine learning often publish an R package to accomplish their articles, meaning that you can have immediate access to cutting-edge statistical techniques and implementations. Another key strength that R has over many other data science tools is its sophisticated graphics capabilities. R is able to create beautiful and publication-quality graphics. R's base graphics system gives the user very fine control over how graphics are created. Other newer plotting systems, like the grammar-based ggplot2 system, allow for more complex and sophisticated visualizations and shortens the distance from mind to page. This figure is a reproduction of a graphic from The Economist based on some public data. Clicking it will lead you to the original figure. You can compare it with this reproduction, and we'll learn how to do so when introducing the ggplot2 library. Data analytics work performed with R can be saved as scripts so as to be easily executed at any moment. This is a key feature that facilitates reproducible work in R. R also provides powerful tools for communicating our results. For example, R Markdown makes it easy to turn our results into HTML files, PDFs, Word documents, PowerPoint presentations, and more. Actually, all slides used in this course are created from R Markdown files, and all your in-class exercises and assignments will be delivered in form of R Markdown files. We'll learn some basics of R Markdown momentarily. There is also an R package called Shiny that allows us to make beautiful interactive apps without any knowledge of HTML or JavaScript, as shown here. We can use these two sliders to change the intercept and slope to fit the data with different straight lines. And this app also includes pans that shows overall model fittings and checks the normality assumption of error terms. R is also easy to integrate with other tools. Many cloud machine learning and deep learning services support R as one of their interface languages. R can also be used on high-performance clusters to handle complex and large data and perform big data analytics. Because of these strengths, R is quickly becoming the standard language for statistical and data analysis. As you can see in this graph, R is one of the top 5 languages asked for in data scientist job postings. And note that, except R, all the top 5 languages are general-purpose languages, which in theory have broader applications. In this course, we are going to learn how to use R programming to address business analytics and data science problems. To start, I would like to first give you an overview of how R will fit into a workflow that carries out a business analytics and data science project. Every project starts with some business question that is to be answered with data. Once the question is solidified, we can start this process by first finding and generating the data we are going to use to answer that question. This typically means that we take data stored in a file or database, retrieve data via web API, or even scraped raw data from web. And then we must import the data to R. Once we've imported the data, it is a good idea to tidy it. Tidying the data means storing it in a consistent form in which each column is a variable and each row is an observation. Tidy data is important because the consistent structure lets us focus on questions about the data, not fighting to get the data into the right form for different transformations. Once we have tidy data, a common first step is to transform it. Data transformation includes narrowing on observations of interest, creating new variables from existing variables, and calculating a set of summary statistics. Once we have tidy data with the variables we need, there are two main engines of knowledge generation: visualization and modeling. Visualization is a fundamental activity of data exploration. A good visualization may show us things that we did not expect or raise new questions about the data. Once we have made our questions sufficiently precise, we can modeling the data, which means using some statistical or machine learning techniques to analyze the data and answer our questions. The last step of data science is communication. The finding has to be communicated to others. Sometimes this is a report you send to your boss or team at work. Often it's a presentation to a group of colleagues. Surrounding all these tools is programming, which is a cross-cutting tool that we use in every part of the project. Next, I will go through several class examples to explain the role of R in these steps. The first example is about getting data from the web. Since his 2016 presidential campaign started, Donald Trump has sent thousands of tweets into the world. Because his tweets are a useful time capsule for his campaign, by analyzing his tweets, we can see what Trump talked about the most, what people suffered the majority of his attacks, and how Twitter reacted to what he was tweeting about. To do so, we need to first collect Trump's tweets from Twitter. Twitter actually provides application programming interfaces, or APIs for short, which developers and data analysts can use to access the platform's data. There are several R packages for interacting with Twitter's APIs. And here we are going to use RTweet. Then, fetching status data posted to the timelines of a Twitter user is as simple as writing a single line of code. The newly collected data could be a mess and lack variables that are critical for answering the questions we are interested in. So we need to arrange data in a way that makes it easier to work with and transform the data to create useful variables. There is a popular suite of tidy tools in R, known as the Tidyverse. The tools in Tidyverse share a common underlying design philosophy, as well as grammar and data structures, and work together naturally. They provide us with a cohesive way to wrangle our data and also allow us to transition smoothly from the data wrangling stage to subsequent stages of data analysis. Using data wrangling operations provided by Tidyverse, we can organize the data into this nice table. We may want to do some further text analytics to extract some key information from these tweets to, for example, figure out which candidate suffered most from Trump's attacks. As a picture is worth 1,000 words, with R, we can create an informative and aesthetic graphic to show how Trump's most formidable rivals changed as the campaign went by. This figure is created by the ggplot2 library, which will be one of our main topics of this course. Being able to work with geospatial data is also an integrated part of R's great visualization capabilities. This Choropleth map is created by the ggplot2 library with some map data. It visualizes the county-level result of the US 2016 presidential election. This is going to be one of our LAM or in-class exercises. In addition to simply counting specific terms in a text, we may also want computers to perform more intelligent tasks as humans do. For example, when approaching a text, we can use our understanding of the emotional intent of words to infer sentiments expressed in a text. Here are 2 user reviews along their star ratings from the IMDb website. One person assigns a movie a 10 out of 10 score, implying that she is very enthusiastic about the movie, while the other user gives another movie 4, which is considered slightly negative. But that's all that can be inferred from numerical ratings, because numerical ratings are unable to represent subtle or nuanced emotions like boredom, absurdity, surprise, or excitement. This is where text-to data counts for a lot. Nowadays, text-to data is everywhere online and is a wonderful resource to mine. Once we can teach computers to understand texts, we can then drive them to read thousands or even millions of texts. To learn, for example, the general public's opinions on your firm's products or services, as computers are extremely good at repeating things. But online texts are primarily provided in HTML format and not readily available for us to use. HTML web pages mixed the content we care about with massive amounts of formatting tags that define how content should be presented in terms of, for example, the font size, font color, positioning, etc. Here I use the Chrome's Developer Tools feature to show you the raw details of an IMDb user review page. It demonstrates how movie reviews could be buried in enormous tags. So before performing any meaningful analysis, we need to first extract relevant contents and drop unnecessary tags from a web page. This is called web scraping. The tricky thing is, although HTML tags are irrelevant and annoying, they could be helpful for us to locate textual data that we are interested in. Observing that movie reviews are actually enclosed by a special class of div tags, we can use an R package named rwest to locate these HTML nodes and further extract content wrapped within them automatically. And with R, we can even make web scraping step into a higher level of automation. That is, when working with dynamic web pages whose contents are dynamically rendered, we can use R code to drive a browser to mimic clicking on these icons to load contents dynamically as a human being would. This technique is called dynamic web scraping and will also be covered in this course. In your final project, you may need to use this technique to scrape textual data from the web. All right, that's all about the preview of our planned topics. Next, let's talk about how we can get started with R. One of the most popular ways to run R has become RStudio, which is a free, open source, integrated development environment for R. As you can see from this screenshot, RStudio ties 4 main windows on the screen. It has a nice editor with syntax highlighting, a console to execute our code interactively, and there is an object viewer and a number of other useful panes. In recent updates, a support for Python has also been built into RStudio, making it an ideal environment for data scientists who want to leverage both R and Python, the two most popular languages for data science, in their data science projects. RStudio is going to be the main environment for doing programming and reporting in this course. Please follow the instructions in this guide to install first R and then RStudio, as RStudio is a graphic user interface on top of R. Once RStudio is successfully installed, watch this R2 video to get yourself familiar with its layout and functions. When we attempt to perform data or business analytics in a programmatic way, there are often many different steps, which involve a lot of coding and computing, and perhaps different kinds of data manipulation, visualization, and modeling. It's important that when we communicate what we've done, we can communicate in a way that someone else could actually reconstruct what we've done, so that's reproducible by someone else. Reproducibility is a very important aspect of any data analysis or business analytics deliverable. So next, I'm going to talk about the basic tool that we are going to use in this course to help make our analysis and work in general reproducible. That is R Markdown. R Markdown is a specialized Markdown format, which allows us to embed chunks of our code and their results in narrative text, and mark up narrative text with an easy-to-write formatting syntax. R Markdown provides a unified authoring framework to combine our code, its result, and our pro commentary, and turn our analysis into high-quality documents, reports, presentations, and dashboards. R Markdown documents have the conventional extension RMD and are fully reproducible. They will be used as main format for our lab and in-class exercises, as well as homework assignments. When you open an R Markdown file, it will be displayed in RStudio's source window. An R Markdown file begins with a header surrounded by a pair of triple dashes. The header is used to include metadata about the document, like title, author, date, and more importantly, output formats into which this R Markdown file can be rendered. Here I specify the HTML document as output format. So when I click this neat button later, An HTML document will be created from the R Markdown file. Following the header is the document body. We use it to weave our R code and narrative text together. In the document body, chunks of our code are introduced by surrounding each with a pair of triple backticks. This R in the curly braces specifies the language of the code and can also be followed by a name for this chunk. Here, setup, and options that indicate how the code and its output should be rendered in the output documents. For example, here I set this include option to false, meaning that when turning this R Markdown file into an output document, the rendering process will run the code, but neither the source code nor its output will be included in the output document. And in the second chunk, by setting this echo option to false, I indicate the rendering process to only exclude the source code from the output document. So the output of this code, which is a figure, will be displayed in the output HTML file. You can find other languages R Markdown supports by clicking this Insert button. Between these two chunks of code, I insert a parenthesis to comment what I'm doing. Here I use a pair of single backticks to introduce R code directly into the text. Code introduced in this way is called inline code. And they will be evaluated and replaced with evaluation results in the output document. And the plain text can be formatted with the Markdown language, whose syntax is easy to pick up. You can find a quick reference in the drop-down menu under Help. Please download and play with this R Markdown file. Remember to install the tidyverse collection before you need it. And the rendered output should look like what is shown on this slide. And this slide just gives a summary of what we've discussed about R Markdown. Lastly, I would like to spend some time discussing the course mechanics. Due to the university's needs to adopt online teaching in this winter term, it's a pity that we cannot have face-to-face class meetings and interactions. But we can take this chance to apply the flipped classroom strategy, which proves to be a better approach for programming courses than an instructional one. This approach focuses on hands-on training and provision of individual feedback to help students succeed. So it perfectly matches the nature of programming courses, which typically require students to spend significant, dedicated time practicing programming in order to be successful. In order to tackle this novel situation and implement this strategy, I've been making an overhaul of this course. Here is the detailed plan. In the morning session, you are required to watch online lectures on designated topics, and the afternoon sessions are primarily reserved for in-class exercises. There will be 9 in-class exercises in total, accounting for 30% of your course grade. In-class exercises are well designed to assess your understanding of concepts learned from video lessons and provide you opportunities to apply them into practice. They also give you opportunities to explore specific topics in greater depth and serve milestones to conclude learning outcomes on a daily basis. As individual feedback is crucial for helping you resolve potential misconceptions, I will spend the time working with you in afternoon sessions while Zoom meetings. You can call in Whenever you are in need of more explanations and clarifications on lecture contents, or run into problems during working on in-class exercises. And there are parallel lab sessions. During the lab sessions, you will get hands-on practice with lecture concepts by working on lab exercises. Labs will be delivered via live Zoom meetings, and participation is mandatory unless you have legitimate reasons for absence. There will be 10 labs in total. Your lab participation score will be calculated based on the number of labs that you submit. And the 2 individual assignments will be given as the term progresses. Each possibly comprises conceptual questions to be answered and hands-on tasks. These 2 individual assignments will give you chances to apply what you learned to solve longer and more complex problems. There will be no final exam. Instead, you will have a group project which asks you to apply R programming to solve a designated business problem. And the project will start from getting data from the web through performing some predictive modeling with data. The detail will be announced in the 3rd week, and the workload should be reasonable. You will be given approximately 2 weeks to work on it. Each group should have no more than 3 members. Otherwise, there will be significant coordination costs, given that we are using online learning. You can first try to form groups by yourselves. If you have problems regarding group formation, let Charles know. He will help you find group mates. And make sure your contribution will be acknowledged by your group mates, since 10 out of 30% of your final project grade will be based on peer evaluation. And I would also like to talk a bit about what are considered the bounds of collaborations for a coding class. Actually, you are encouraged to discuss course materials with your classmates and learn from each other or the internet. However, all work you turn in must be your own. This includes both written explanations and code. Copying from other students, books, or websites does nothing to help you learn how to program, and could also have serious negative consequences for you. There are some details about the collaboration policy in the syllabus. Please take some time to read them. And please also read the grading rubrics stated on the syllabus carefully, since it will apply to all of your submissions. In the very end, I would like to say, there are many reasons that make your feedback extremely valuable in this term. Because of the distance teaching, because of the new design of this course, because programming is hard in its nature, and many more. Your views and perspectives need to be shared, and our teaching team will try our best to address any of your concerns. Thank you.